Hi dear students, welcome back to the next session on proteins. In the previous session, we had discussed about the different types of amino acids and how amino acids are joined together, resulting in the formation of proteins. Now let's talk about the physical properties of amino acids. Amino acids, as we all know, they combine together to form the peptides. And the peptides are folded in different ways, resulting in the formation of functional proteins. Now, these amino acids, which form the part of proteins, they are being found to be colorless crystalline substances. But the crystal form would vary from different amino acids. Now, some of them would be slender needles, as in the case of tyrosine, or sometimes they might be found to be thick hexagonal plates, as in the case of cysteine. Okay, and so the crystal structure of the amino acids will be found to be different. Now, coming to the taste, sometimes they might be sweet, as in the case of glycine and alanine, or they might be tasteless, as in the case of tyrosine, bitter, as in the case of arginine, and you can see that in the S-alanine, phenylalanine, it has been found to be bitter in taste, but its an enantiomer R phenylalanine has been found to be sweet. Now, what is R and S? It's just another notification of the DL isomers, as we had already discussed earlier. So R refers to the D and D isomer, and S refers to the L isomer. Amino acids, they have a melting point about 200 degrees centigrade, and at high temperatures usually they get decomposed. And regarding its solubility, you can see that amino acids, they are soluble in polar solvents such as water and ethanol, but they are insoluble in non-polar solvents such as benzene and ether. And if you go to analyzing some amino acids, some of them which are having aromatic ring and all that. Now, for example, tryptophan, tyrosine, and histidine and phenylalanine, they are having an absorption maximum. That is, they can absorb ultraviolet rays at 260 to 290 nanometer. And hence, if an amino acid is absorbing UV light at that particular range, we can, if a protein, you can say that at that particular region, it is made up of those amino acids. Now, for example, this is a depiction. If you take the different wavelengths of light over here and the absorbance, tryptophan is having a high absorption peak over here. Tyrosine is also having, and you can see in the case of phenylalanine also, a small peak is coming at the range of 260 to 2D. But the intensity of absorbance will be found to be different in the case depending upon the concentration of the amino acid also. So they are capable of absorbing light at 260 to 290 nanometers. So you can say such amino acids could be present in the proteins when they are having an absorbance at that particular range. Now, next we're going to talk about the hydrophilicity, or the water loving nature of the amino acids. You can see that amino acids like tyrosine, serine, aspartic acid, glutamic acid, asparagine, glutamine, and arginine, they are been found to be hydrophilic amino acids. Amino acids such as phenylalanine, alanine, valine, glycine, leucine, and cysteine, they are being found to be considered to be as hydrophobic amino acids, and the range of their hydrophobicity is also being found to be depicted in the picture, with phenylalanine having more hydrophobicity than alanine and cysteine and all. Okay, now we're going to talk about the electrochemical properties of amino acids. We all know that all the molecules possessing both acidic and basic groups exist. They might exist as uncharged molecules or in ionic forms or a mixture of both. And calculations have revealed that in an aqueous solution, most of the amino acids, now for example glycine, they mainly occur as ionic forms rather than in occurring in the non-ionic form. Now coming to amino acid, it is having a NH2 group over here, a acidic group also, as well as a basic group. But when it is in a solution, it does not exist, like it prefers to be existent to be as an in this ionic form, where COOO minus is written and the proton is being given to NH2, resulting in the formation of NH3 plus. So as a result, all the amino acids, their structure, when though we write them as COOH and NH2 in their chemical formula, when it comes to the solution in aqueous solutions, most of them they will prefer, okay, what prefer to be occurring in the charged form or in the ionic form. And amino acids, they react with both acids and bases, and in such a case, we call them to be as amphoteric in nature. Now, an amino acid, when it reacts with an acid, it can form like this. It can liberate the anion, and it can receive the proton, resulting in the formation of RCHCOH at NH3 plus. And at the same time, if a base is coming over here, it will accept what if a base has been added, it will not accept it. It donates a proton towards that side, resulting in the formation of water. Thus, in acid solution, the COO minus ion acquires a proton, and the amino acid becomes an ammonium salt of the acid. And in the alkaline solution, the ammonium ion loses a proton, and the amino acids become an anion of the particular salt. And so these reactions are of reversible nature, and it is also dependent upon the pH of the medium. So since it can accept both acid and base, amino acids can serve as buffers, and they tend to prevent the pH change when an acid or a base is being added to the solution. Now, the next thing what we have to discuss is about the titration of amino acids. But before going into the titration of amino acids, I would like to talk about I would just have to recollect you regarding your basics regarding pH. Of course, we know what is pH. pH is nothing but the negative logarithm of the hydrogen ion concentrations which have been present in a solution. So if it is in fact giving us a simple index of expressing the H plus level or the proton level. Okay, and if you have a smaller number, that means if the pH value is being found to be very low, it indicates that there is a higher proton concentration. So one important point regarding pH is that a change of only 1 in the pH value is equivalent to a 10-fold change in the proton concentration. So when you indicate by a value by pH, now we have pHs from 1 to 14. So a pH of 1 means it is highly acidic. Okay, the proton concentrations are being found to be very much high. Okay, and when it comes to 6, the pH is being found to be higher, but the proton concentration is being found to be lesser. But when you go to 7 and above, what is it? The proton concentrations are becoming lesser. So pH is something which helps us to identify the what? The proton concentrations which are being present in a solution. Now acids, it can include strong acids which are completely dissolved in water, and also weak acids which can be partially dissociated. Now, when an acid dissociates, it will release a proton to make a solution acidic. But a weak acid have both dissociated state and an undissociated state. And as a result, what happens? They will exist in a what? Equilibrium with each other. That is, if it's a weak acid, it can occur as A minus. Normally, it is all acids will dissociate like this. But if it's a weak acid, it will also have a weak undissociated state called the AH, as well as also the dissociated state A minus and H plus. And the concentration ratio of both the sides is a constant given at a fixed analytical conditions, and it is referred to as the acid dissociation constant. So a constant called the rate of the dissociation is being determined by a Ka factor called the dissociation constant, that is equivalent to the concentrations of A in the dissociated ion A minus and the dissociated ion H plus divided by the undissociated concentration. So this ratio gives us a constant where, and it is a ratio of the concentration that is called the Ka. Now, I'm going to talk about, we spoke about we spoke about pH. We are talking about the dissociation constant Ka, which is equivalent, this is applicable for the weak acids. In the strong acids, of course, they would be totally be dissociated. But in the case of weak acid, they also occur as undissociated forms, and the dissociation constant is as shown like here. Now, let's move on. If you go to consider carboxylic acids, now for example COOH, as in the case of acetic acid and lactic acid, they have a Ka constant of about 10 raised to minus 3 to 10 raised to minus 6. So, consequently, expressing the acidity in terms of Ka constant alone can be inconvenient and not very intuitive. So therefore, now if you go to express the constant value, we started using a pKa as an index to express the acidity of the weak acids. Now, what is pKa? pKa is a negative logarithm of log 10 Ka, negative logarithm of Ka. Now, the Ka constant of acetic acid is 0.000, not 0.000158 or 10 raised to minus 4.8, but the pKa constant is 4.8. So to express, just like we have the hydrogen ion concentrations expressed as pH, like that, the concentration of, or the dissociation constant of each weak acid is expressed as a negative logarithm of the Ka value as pKa. So if this value, the previous value, you get the Ka value, that Ka value is being expressed as pKa to check the to express the acidity level of weak acids. Now, in the case of lactic acid, the pKa value is 3.8. So that it means that lactic acid is stronger than acetic acid. So lower the pKa value, it indicates that the it's more is its acidity. Just like pH in the case of strong acids, the same way in the case of weak acids, we take the what? We take the pKa value to check its acidity. Now, so pH and pKa, they are simple convenient notations for proton concentration. pH is for proton concentration and pKa is to determine the equilibrium constants of ionization. And pKa is a measure of the tendency of a group to give up a proton with that tendency which is increasing tenfold as the pKa increases by 1 unit. So I hope you got an intense idea of it. pH gives us, it's for the strong acids, and it gives us the amount of protons present, and pKa is the it's usually used for the weak acids and it gives us an estimation of the tendency of that particular substance to give a proton. The lower the pKa value, it means it has been found to be more acidic in nature. So keeping this in mind, let's observe acetic acid. In this case, you can see that if the solution's pH changes near 4.8, okay, it causes a large change in the presence of acetic acid. Now, you look at the pH between 1.8 to around here, okay, about 4.9, you can see the component will be found, acetic acid will be found as CH3COH. But at a temperature beyond that, 4.9 to 7.8, you can see that the more predominant one, it mainly occurs as CH3COO minus. So, a change in the pH level, and look at this particular point, at 4.8, around the middle point, you can see that there will be an equilibrium between these two. That is, Equal concentration of CH3COH and COOH will be found at a point around 4.8, around here, at these regions beyond the, so at this pHs. Now for between 3.8 to 5.8, there would be equal concentrations of, they will be having a equilibrium. So a change in the pH, okay, near the pKa value of an acid. So this is referred to, and you should remember pKa value is the particular, it refers to pKa value will happen, or that particular this thing will happen at a pH which is, this is a pKa value. So at a pH near to the pKa value of this thing, both the ions will be at an equilibrium and they will be having what do you say, equal concentrations. So at that particular pHs, or the pHs closer to the pKa value, such solutions will be considered to be as good buffer solutions. That is, even if you add a little bit of acid or little bit of alcohol, they will try to buffer it, or the buffering capacity of a solution will be very much high if the pKa value and the pH value is being found to be close to each other. Okay, so that's it. The buffer solutions with a pH equal to the pKa value of the acid have the greatest buffering capacity. So if you add something at if you want to a buffer to act between 3.8 to 5.8, you can take, okay, if you want to maintain if you need a buffer which has to act at this particular range, since acetic acid is having a pKa value at that particular range, you can use acetic acid as a good buffer in that particular range. So I hope you got the concept of pH and the pKa. pKa is nothing but what, it is a ionic dissociation constant. Okay, and if the pH is equivalent to pKa, that means the at the pKa value time, what happens, the ionic concentrations of these two will be the similar. That is the dissociated form, and the undissociated form would be the same. Now let's explore the titration curve of certain amino acids. If you look onto this figure, you can see that it is a titration curve at which, of course, the moiety alanine is the amino acid which we are having here. You are adding different concentrations of OH equivalents, and you are checking the pH also. Okay, these are the plottings. So if you go to look into this, you can see that the plot is having two distinct stages over here, and each is corresponding to the removal of one proton from alanine. Now look at the values over here. Now you can see at this particular pH, okay, at this particular pH corresponding to 2.34, there is a equal concentration of about, now it is occurring as, now the concentration of NH, this one, what, the alanine, the protonated form of alanine is equivalent to that, the COOH form and the COO minus form, that is being found to be equivalent. That is NH3CH CH3COH and the proton acceptor NH3 plus CH CH3CO minus, they are equally present. So at this particular point, the pK1 2.34, there are equal concentrations of the, what do you say, the proton acceptor and the proton donor, which is the, this is the proton donor and this is the proton acceptor. Okay, so you can see as the OH equivalents are being, of course, the pH is being changed by using hydroxyl equivalents over here. So as the pH is being changed, now for example, when you increase the hydroxyl quantity, the pH will be found to be increasing, you can see. So when it has been increased and when the pH becomes around here 2 point something, you can see that they are at equal concentrations. And so the midpoint of this titration, where the pH is equivalent to the, they are in equal concentration, means that is their pKa value. Okay, so this is 1 pK1. Okay, and for alanine, the pH at the midpoint is 2.34. Thus, its COOH group has a pKa of 2.34. Now, if you go to look further as the titration proceeds, you can see at a pH 6.02, okay, there is a point of inflection at which there is a what? There is a removal of what? A proton. See, from here, in the first case, what it was completely protonated, diprotonated, like at the NH3 end and at the COH end, there was protons. And when the as the pH was increased, what happens? The proton was being removed and it became COO minus. Now, when the pH is again increased, what happens? It has become NH3CHCOO minus. It is complete over here. There is a point at which the removal of the first proton is totally complete. That is, this removal of H plus is at 6.02. It is having the complete removal of H plus is complete. Okay. At this pH, alanine is present as a dipolar form. So at this particular pH, you don't have these two forms, only at one particular form alanine is being found. So it becomes a totally what? A dipolar form, and the net electric charge is being found to be 0. Now again, when you titrate it, you can see that what happens. You can see the proton removal from NH3 plus has to be done, and there is another value at which there's another pH, okay, at which the NH3 plus CH3COO minus, the concentration of that is equivalent to NH2CH3COO minus. So the pH at that particular time is, or the midpoint of the pH at the midpoint of this stage is 9.69, and it is equivalent to the pKa of the ammonium group or the NH3 group. So the titration then again is completed by 11.69, at which point the molecule alanine bears a net charge of -1 because both the functional groups are being found to be deprotonated. And 99% of the molecules are negatively charged and are present as NH2 CH3COO minus at this particular range of about 11.69. So the pH value 6.02, at which the average net charge is 0, that is called the isoelectric point or the isoelectric pH. So it is a midway between the two pKa values, 2.35 and 9.69 divided by 2. So you should remember at a particular pKa value of 2.34, the concentration of what? Two ionic concentrations, like two ionic derivatives, like NH3 plus CH3 and COOH, is the concentration of that particular form of amino acid is equivalent to NH3 plus CH to the deprotonated. They are equivalent over here. This is the pKa value for the COO group. Okay, and that is equimolar concentrations of those two ionic forms are be present at that particular pH. And if you go towards here, again when the pH is being increased, what happens? There is a stage over here where the concentration of the two forms, here the protonation, the removal of proton has been carried out from the NH3 plus group. So NH3 plus group has been converted into NH2. So there also you have a pKa for the ammonia group of 9.69. But in between these two, there is a point at which the amino acid will be found to be electrically neutral. Because what? As the pH is being increased, okay, what happens? The amino acid is occurring only in this particular form at this particular pH. So this point at which it occurs as a electrically neutral stage is considered to be it as a what? That is mainly considered to it as a isoelectric point. Now, why do you have to study this titration? Now, by studying the titration curve, you will get an idea about the pKa values of each two ionizing groups. Like you get 2.34 for COH group and 9.69 for NH3 group in the case of alanine. And it also gives us an information that it has this particular substance has two ranges of buffering activity. That is, it has a pKa value at 2.34, and also it has a buffering pKa value at 9.69. So I told you every substance can act as a good buffer at a value which is equivalent to its pK at the range of it. So it can serve as a good buffering agent between the pHs around what happens, one is around at 2.34 and also at 9.69. And it also gives us the information regarding the relationship between the net electric charge of the amino acid and the pH of the solution. Now, for example, we know around a pH of 6, the amino acid will be been found to be as electrically neutral. So once you get both the pKa values, at which particular pH will it be electrically neutral? That is, now for example here, it is 2.34 plus 9.69 divided by 2. At the midpoint of that, you will get the isoelectric point of the particular amino acids. So these are some of the characters which I would like to talk about the physical properties of amino acids. Thank you for now.